Hello, today we will have the second lecture of our discrete mathematics course. We will cover the language of sets, subsets, and Cartesian products. These concepts are very important because all other topics we will cover in this course are built upon these concepts. Please like the video and subscribe to our channel. We start with the concept of sets. The use of the word set as a formal mathematical term was introduced in 1879 by George Cantor. As we will see later on, sets are fundamental mathematical structures. Almost everything in math revolves around sets. For most mathematical purposes we can think of a set intuitively, as Cantor did, simply as a collection of elements. Let S be a set. The notation, X belongs to S, means that X is an element of the set S. The axiom of extension says that a set is completely determined by what its elements are, not the order in which they might be listed or the fact that some elements might be listed more than once. For instance, the set with elements 1, 2, and 3 is the same as the set with elements 3, 2, and 1. Which means that the order of elements is not important, but it is the elements themselves that form a set. They can be listed in various form but it will not change the core structure of the set. Let us look at this first example. In this example, questions are stated as follows. Question A. Let A be the set with elements 1, 2, and 3, and the set B be the set with elements 3, 1, and 2, and capital C be the set with elements 1, 1, 2, 3, 3, and 3. What are the elements of A, B, and C? Moreover, how are the set A, B, and C related? Question B, is the singleton with element 0 equals 0? Question C, how many elements are in the set with two elements, 1 and the singleton with only element 1? Question D, for each non-negative integer n, let un be the set with elements n, and negative n. Find u1, u2, and u0. Now, let us go over the solution to this first example. By addressing these questions, we will clearly review the intuitive concept of elements of a set. For question A, we see that A, B, and C have exactly the same three elements, 1, 2, and 3. Therefore, A, B, and C are simply different ways to represent the same set. We therefore see that these sets are equal to each other. In question B, the singleton with only element 0 is not the same as 0, because it is a set with one element, namely 0, whereas 0 is just the symbol that represents the number 0. In question C, the set with elements 1 and the singleton 1 has two elements, 1 and the set whose only element is 1. D. In question D, the set U1 has two elements 1, and negative 1, the set U2 has two elements 2, and negative 2, and U0 is a singleton with only one element 0. Let us talk about some classical sets of numbers that we have or will encounter in other fields of mathematics. These sets of numbers are so frequently used that they are given special symbolic names. R denotes the set of all real numbers. Z is the set of all integers. Q is the set of all rational numbers. N is the set of non-negative integers or natural numbers. The set of real numbers is usually pictured as the set of all points on a line. The number 0 corresponds to a middle point, called the origin. A unit of distance is marked off, and each point to the right of the origin corresponds to a positive real number found by computing its distance from the origin. Each point to the left of the origin corresponds to a negative real number, which is denoted by computing its distance from the origin and putting a minus sign in front of the resulting number. The set of real numbers is therefore divided into three parts: the set of positive real numbers, the set of negative real numbers, and the number 0. Note that 0 is neither positive nor negative. Let S denote a set and let P of X be a property. We may define a new set as the set of all elements X in S such that P of X is true. We denote this set as follows: the set with elements X in S such that P of X is true. Now, let us look at the second example. The set R denotes the set of all real numbers. Z is the set of all integers, and Z plus the set of all positive integers. Describe each of the following sets. Question A. Describe the set of x in R such that -2 is less than x, and x is less than 5. Question B. Describe the set of x in Z such that -2 is less than x, and x is less than 5. Question C. Describe the set of x in Z plus such that -2 is less than x, and x is less than 5. For question A, the set of real numbers between -2 and 5 is the open interval of real numbers, strictly, between -2 and 5. It is pictured as follows. For question B, the set of integers strictly between -2 and 5, is equal to the set with elements, -1, 0, 1, 2, 3, 4. For question C, the set of positive integers strictly between -2 and 5, is equal to the set with elements 1, 2, 3, 4. Now, let us study the concept of subsets. If A and B are sets, then A is called a subset of B, if and only if every element of A is also an element of B. In other terms, A is a subset of B, which means that for every element x, if x is in A, then x is in B. It follows from the definition of a subset that, for a set A not to be a subset of a set B means that, there is at least one element of A that is not an element of B. In other terms, A is not a subset of B, if there exists an element x in A, such that, x is not an element of B. A is a proper subset if, and only if, every element of A is in B but, there is at least one element of B that is not in A. Example 3. Let A be equal to Z plus, the B be the set of integer n such that n is greater or equal to 0, and n is less or equal to 100, and the set C with elements 100, 200, 300, 400, and 500. Evaluate the truth and falsity of each of the following statements. Question A, B is a subset of A. Question B, C is a proper subset of A. Question C, C and B have at least one element in common. Question D, C is a subset of B. Question E, C is a subset of C. Solution. Statement A is false, 0 is not a positive integer. Thus 0 is in B but 0 is not in A, and so B is not a subset of A. Statement B is true. Each element in C is a positive integer and, hence, is in A. Moreover, there are elements in A that are not in C. For instance, 1 is in A and not in C. This proves that C is a proper subset of A. Solution. Statement C is true. For example, 100 is in both C and B. Statement D is false. For example, 200 is in C but not in B. Statement E is true. Every element in C is in C. In general, the definition of subset implies that all sets are subsets of themselves. Now let us look at example 4. Which of the following are true statements? Question A, 2 is an element of the set with elements 1, 2, 3. Question B, the singleton 2 is an element of the set with elements 1, 2, 3. Question C, 2 is a subset of the set with elements 1, 2, 3. Question D, the singleton 2 is a subset of the set with elements 1, 2, 3. Question E, the singleton 2 is a subset of the set with elements the singleton 1 and the singleton 2. Question F, the singleton 2 is an element of the set with elements the singleton 1 and the singleton 2. Only A, D, and F are true. A is true because obviously 2 is an element of the set with elements 1, 2, and 3. D is true because the singleton 2 is of course contained in the set with elements 1, 2, and 3. F is true because the singleton 2 is clearly an element of the set with two elements, the singleton 1 and the singleton 2. For B to be true, the set with elements 1, 2, 3 would have to contain the element, singleton 2. But the only elements of the set 1, 2, 3 are the integers 1, 2, and 3. Moreover, 2 is not equal to the singleton 2. Consequently, B is false. For C to be true, the number 2 would have to be a set and every element in the set 2 would have to be an element of the set with n elements 1, 2, 3. This is not the case, so C is false. For E to be true, every element in the set containing only the number 2 would have to be an element of the set whose elements are the singleton 1 and the singleton 2. But 2 is not equal to either the singleton 1 or the singleton 2, and so, E is false. The last main topic of this lecture is the concept of Cartesian products. Given elements A and B, the couple, AB, denote the ordered pair consisting of A and B together with the specification that A is the first element of the pair, and B is the second element. Two ordered pairs A, B and C, D are equal if, and only if, A equals C, and B equals D. Example 5. Question A. Is the couple 1 and 2 equal to the couple 2 and 1? Question B. Is the couple 3 and 5 over 10 equal to the couple square root of 9, and 1 over 2? Question C. What is the first element of the couple 1 and 1? Let us go over the solutions. For question A, the correct answer is no. By definition of equality of ordered pairs, the couple 1, 2 equals to the couple 2, 1, if, and only if, 1 equals 2 and 2 equals 1. But 1 is not equal to 2, and so the ordered pairs are not equal. For question B, the correct answer is yes. By definition of equality of ordered pairs, these equations are both true, the ordered pairs are equal. Question C, in the ordered pair, 1, 1, the first and the second elements are both 1. The notation for an ordered n-tuple generalizes the notation for an ordered pair to a set with any finite number of elements. It also takes both order and multiplicity into account. For instance, the n-tuple x1, x2, x3, xn is equal to the y1, y2, y3, yn if, and only if x1 equals y1, x2 equals y2, xn equals yn. Example 6. Question A. Is the quadruple 1, 2, 3, 4 equals to the quadruple 1, 2, 4, 3? Question B. Is the triplet 3, negative 2 square, 1/2 equal the triplet square root of 9, 4, 3 over 6? Solution. For question A, the correct answer is no. By definition of equality of ordered quadruple, but 3 is not equal to 4, and so the ordered quadruples are not equal. For question B, the correct answer is yes. Because these equations are all true, the two ordered triples are equal. Given sets A1, A2, An, the Cartesian product of A1, A2, An denoted as follows is the set of all ordered n-tuples A1, A2, An such that A1 belongs to A1, A2 belongs to A2, An belongs to An. Example 7. Let A be the set with elements x, y, and the set B with elements 1, 2, 3, and the set C with elements little a, and little b. Question A, find the Cartesian product A times B. Question B, find the Cartesian product B times A. Question C, find the Cartesian product A times A. Question D, how many elements are in A times B, B times A times A? Let us go over the solution. Question A, the Cartesian product A times B is the set of ordered pairs, x, 1, y, 1, x, 2, y, 2, x, 3, y, 3. Question B, the Cartesian product B times A is the set of ordered pairs, 1, x, 1, y, 2, x, 2, y, 3, x, 3, y. Question C, the Cartesian product A times A is the set of ordered pairs, x, 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 y, y, x, y, y. Question D, the Cartesian product A times B, and the Cartesian product B times A have 6 elements. In fact, this is equal to the number of elements in A times the number of elements in B. The Cartesian product A times A has 4 elements, this is equal to the number of elements in A times the number of elements in A. On this, we end this lecture. Thanks for watching the video. Please do not forget to like the video and subscribe to our channel. We have an extensive collection of mathematics lecture notes covering all sequences of calculus, college algebra, discrete mathematics, and probability. Thanks.